Next month, you can join us for a presentation by Dr. Tanner Adronimus, present on some design aspects of the near-surface tunnels for the Northway Busway in Brisbane, Australia. And as always, you can register for next month's webinar on our events page of the website. And finally, we kick off the 2016 webinar series with a presentation by Mikael Calando on the San Francisco Central Subway. Mikael has 20 plus years, Mikael is an engineer for Nicholson Construction Company. He holds a master's degree in civil engineering from EPF in Paris, France, and University of Maryland, College Park. His experience in some of the most difficult technical techniques of geotechnical construction, including diaphragm walls, jet grouting, seeping tangent piles, and computerized grouting. His duties include design and constructability review, quality assurance, and quality control of the construction operations. In the past 5 years, he's worked on some of the largest tunneling projects in the U.S., including Central Subway, Port of Miami, New York 2nd Avenue, and U220 station in Seattle. Mikael, thank you for presenting for us today. When you're ready, please share your screen.
Hi, thank you, Erin. My name is Mikael Calando. I work for one of the largest geotechnical construction contractors, in the world, Nicholson Construction. It's owned by Soitlange Vashi, which in turn is part of the largest construction, one of the largest construction group in the world, of Vinci Construction. Today, I'm going to present on one of the recent project we completed in San Francisco, the Central Subway project. I'm going to emphasis on the tunneling contract, which is a contract we were awarded. So, as a geotechnical contractor, we work pretty much on everything apart from a tunnel itself. So here's the structure on the team. The owner was SFMTA, which advertised the bid. The contract was awarded to a joint venture of Barnard, Impreglio, and Healy for an amount of about $233 million. And we, Nicholson, as well as our joint venture partner, Con & Johnson, performed and were awarded the specialty geotechnical works for about 20% of the total contract value. So first, let's take a look at the map of the current subway system, or light rail system in San Francisco. The program or Central Subway consisted of extending the current T line, the red line on the right of the screen, to North Beach in Chinatown. So part of the project would be above ground, but most of it would be underground with construction of 3 new stations, the Moscone Station, the Union Market Square Station, that I call UMS a lot, or in the Chinatown Station. On this contract, it was only the tunneling and part of the the headwalls of some of the stations were also part of the tunneling contract. So taking a look at the alignment of a tunnel, you can see it's quite dense urban area. And you can see maybe on the right the I-80 highway, which marks the start of a tunnel and at the end on the left side the retrieval shaft, which marks the end of a tunnel. So again, those 3 stations, the deepest station would be Union Market Square Station. The geology on the project, is important to note that most of the tunnel would be in the overburden, part of the soils, with a small part on the uphill built in the San Franciscan complex melange bedrock. As I mentioned, we as the geotechnical contractor worked mainly around the stations, but also the launch box for the tunnel machine. So I'm gonna marking those, and I'm gonna emphasis quite a bit on those. Taking a closer look at the geology and those key areas, we had fill, dune sands, the bay mud, QM, underfringed deposits, which is the Q layer, the Colma dense to very dense Colma sands, QC, and QO, the old bay clay. So as you can see, the launch box and the Moscone station were keyed into that quite impermeable old bay clay layers. Going along the alignment, we can see the Union Square station and keyed in the old bay clay layer, which is located right after the BART. So the interesting feature on this tunnel is that it would go only a few feet below the existing BART tunnels. So what were we contracted to do on this? Well, mostly it was to work on the structural and supportive excavation walls of the stations, but also the launch box, like I mentioned. So that would be done with diaphragm wall technique, as well as secant and tension power wall technique for the Union Square station. We also took care of the break-in and breakouts of a TBM at the station walls. That would be done with jet grouting. And finally, compensation grouting, which was implemented at key areas to mitigate any possible settlement from the tunneling operations. So today I'm going to talk mainly about the diaphragm wall and what's the supportive excavation and structural walls, so the diaphragm wall and the secant and tension power walls. First, a little reminder or introduction for those who do not know the technique. Diaphragm wall is a technique that came originally from Europe. It's relatively simple to explain. The first aspect, and one of the key aspects, which can be neglected sometimes, is the construction of a guide wall. The guide wall is absolutely key to digging a hole straight. Because, well, like one of the superintendents would say, the way to drill a hole straight is to start it straight. So guide wall is basically concrete, small concrete trench, which would guide the excavation tool in the right location. The second part of it is to elevate with panels with specialized tooling. On the picture you can see here a hydromill, but clamshell or a mechanical or hydraulic clamshell could be used. The excavation is performed under bentonite slurry or polymer to be able to maintain the trench open. The next step, the third step, is the cage placement, the reinforcement placement. So typically with a cage, an interesting aspect also there is to put in place what we call end stop, which are placed at the joints, which are essentially guides to be able to excavate the adjacent panels, keeping a positive connection between the panels with key shaped end stop and joints, but also with water stops to prevent any water infiltration. And the last step is the concreting operation. So the concreting operation is quite key also for this technique. It's similar to piles. It's with tremie placed at the bottom at the excavation, and concrete poured on the hoppers at the hoppers at the top. So in a few words, the launch box consisted of about 100 panels. Sorry, quite large excavation to cover. So when I say the launch box, I'm mainly talking about the, I am talking about the structural and supportive excavation walls. Well, supportive excavation in that case. temporary walls. So one of the biggest challenge at that location, at the launch box, where the TBM would start its journey, was that it would be located right under an existing highway, the I-80 highway, with only about 16 feet of clearance. So you can see the highway there, and all space available. But on top of that, our contract specified to have 2 lanes of active traffic open at all times. So we'd have to work in basically several phases to be able to make sure that clause of the contract was affected, which added for additional challenges. So how did we work on this? Well, the unrestricted part of the launch box was not difficult. It's the unrestricted headroom area would be done with a hydraulic mechanical clamshell, hydraulic clamshell, sorry. But the challenge was working under the highway. Pre-excavation we couldn't find any rig pretty much that could fit under the highway in the local market, or actually in the world pretty much for that matter. And the pre-excavation would be quite difficult, given into account that the water table was pretty high at that area. So we came up with a specialty rig, which was custom made and basically specifically designed for this project. So really, the carrier, which is I want to say a regular Liebherr 855, was available. The clamshell, the short clamshell was available. What wasn't available was the boom to link that whole system together. So we designed internally and manufactured internally that boom to put that rig together. But digging was not the only challenge. Obviously, working under low headroom condition presents a few challenges for the reinforcement placement operation, but also for the concreting operation, because everything could not be placed in one piece. So we adopted a new approach there. We tried to value engineer the current design, and that was done with the help of Bradley Associates for the design of this. Thank you, Eric, if you're listening. Why this new design? Well, what we call SPTC is soldier pile tremie concrete. Essentially, replacing the cages that were in the original design by piles or beams. Those beams presented, that design presented several advantages. One, well, it's easier to splice beams together than numerous pieces of rebar in a rebar cage. The design with beams allowed for a wall that is at least as stiff and in some cases stiffer than the original design with rebar cages. Beams allowed for a simpler trucking and handling than rebar cages. The beams were relatively spaced relatively close together and allowed the concrete to act as legging material between the beams, and therefore we're able to reduce the concrete strength necessary compared to the original design. Another good aspect of using beams is the possibility to use the wet set method. So that would mean that unlike the conventional method is to place reinforcement in the slurry before the bentonite slurry, before the concrete is placed. But that wet set method essentially is placing the pile after the concrete is in place. So that allows for ensuring that there's no risk of incomplete concrete encapsulation or overwall defects. So that was another significant advantage. And the final advantage is that those beams could be used as what I mentioned before, end stops, essentially joints, to guide the excavation of adjacent panels. So despite that new approach adopted and that redesign, digging with such a small tool is difficult. Typically, was mechanical and hydraulic clamshells are much heavier, which helped for verticality. So we used two different systems to control the verticality: an integrated system in the rig, a Lutz system, but also a sonic system called Coden, which enables to view in 3D the shape of a panel and once it's excavated. So that's after the fact. But still leaves room to correct it afterwards, needed. But the digging was not the only challenge. Obviously, even with piles, it was a bolted connection, two splice supplies together, so it could be quite time-consuming, and still having the challenge to work under low headroom. So we had to come up with different approaches and means and methods to counter that. So one of those methods was placing the reinforcement using a forklift and lagging all the beams together so that all the reinforcement of one element could be placed all at one space at one time, and we could maximize the headroom we had available. Another important aspect was to pack out the beam with styrofoam in order to prevent the concrete to go around the beam and essentially be almost an obstruction when excavating adjacent panels. Another important aspect of that construction was to lace the beams all together so that no movement could happen during the concreting operation, or before or after the concrete. Well, no movement could happen when it was placed, pretty much. Extension piles were also necessary, as I mentioned, those piles would be used as end stop as well, and therefore guiding the tool to the bottom of the panel. So those extension piles, even though reinforcement was not all the way to the bottom of the excavation, those extension piles were installed to the bottom of the excavation in order to guide the excavation tool all the way to the bottom, and basically, yeah, to get it and control verticality better that way. So I'm going to talk briefly about Moscone Station as well. That was an interesting topic. So on this contract, I guess the construction was the scope was only to build the headwalls. So we had only 8 panels to build, but that created a few challenges in itself. When we look closer at the design, first of all, in the pre-construction phase, we had the concerns from a constructability standpoint about the congestion in the rebar cage. This was not designed to allow the concrete to flow optimally throughout the cage. So that's a very important aspect, as if the concrete doesn't flow well in the cage, well, there could be some cavities or some voids that could start to happen, where the concrete starts to go around and we have voids in the final structure. Contrary to the launch box, this structure was part of a permanent wall structure. Another aspect we looked at also is the shape of a panel, the geometry. The geometry of the panel did not account for the excavation tool dimensions, and therefore was not optimized to maintain the verticality specifications. On top of that, the cages in the head wall included fiberglass, a section of fiberglass to allow for the TBM to cut through that cage at a later stage. So those panels were installed ahead of the TBM, obviously, and allow for only 3 inches of clearance. So there were a number of challenges that we addressed with the owner-designer, and we worked hand in hand together to fix all those issues and produce well, ensure our success during the construction. Well, one of those challenges from a means and method standpoint was lifting and placing was large L-shaped cage. As you can see here, it's in the middle of the city, pretty close to adjacent structures, and requires 2 cranes pick, and especially specifically made a pick plan, engineered pick plan for that. The rigging was also quite challenging, and it was an L, and the L shape, and basically would the cage would have a tendency to rotate on itself. And again, on top of that, we were very close to the sidewalk and building structure, which didn't make all the neighbors very happy. So that's it for Moscone. That was some of the main challenges. On Union Square, the main challenge was those piles to be built. They were inclined piles as part of the design. Again, it was the headwalls of a station with only a few less than 50 piles to be built, and about 16 of those piles were inclined, about 5 degrees. So at Union Square, obviously, it was also quite a challenge from a space standpoint. Originally, the contract called for leaving 2 lanes open, which was simply not optimal for the construction process. So we convinced the city to let us close the whole street in exchange from some schedule savings. For the construction of those piles, we used 2 different drilling techniques. One was a rotator with a grab on the left. So the rotator would advance the casing down to the final elevation, and the grab, which is attached to a crane, would dig inside that casing, and that's the whole process of the excavation for the piles. We found that technique to be quite time-consuming in the all-day clay, as it was a bit too stiff for that grab to be able to excavate optimally, in optimal manner. So we changed the technique to using a Bauer BG40 rig, which is a Kelly bar rig, and had oscillator built into the setup. So the oscillator would still install the casing, and the Kelly bar rig would drill inside that casing. So the challenge on those on this station was, like I mentioned, the inclined piles, especially from a verticality standpoint. So we came up with a system, well, which is upside down on this slide for whatever reason. We used, we looked at several verticality measuring system. The coding that we used previously on the launch box, for instance, could be used for the regular straight piles, but the vertical piles, but for the inclined piles, it wouldn't work. So we used a slope indicator that we basically we created that jig, which would centralize that slope indicator into the pile and able to give us readings throughout the excavation. Because the key for those survey tools that have inclinometers in them is centralization. So I'm going to conclude quick on this. I guess the main aspect that I will remember from those works was, one, coming up with innovative approaches such as the low headroom clamshell, or also some value engineering aspects to be able to overcome those urban challenges. But also, I'd like to note the important collaboration that was between designers and specialized contractors. Nicholson is one of those only geotechnical contractors that have an in-house engineering department. And we like to get involved as early as possible on projects and talk with designers as early as possible in the design stage to come up with best industry practices recommendations and the constructability and feasibility analysis. So thanks to all this collaboration, we managed to put that challenging project to fruition. So really, that's it for that part of the central subway construction. Wanted to point out that we are hiring, and don't hesitate to, we're always looking for good talent and good people. So if some of you are looking for jobs, don't hesitate to contact me directly. Well, look at our website first and contact me directly for questions and how to apply. Thank you very much.
Thank you, Mikael. What a fascinating presentation. At this point in time, we'd like to ask our attendees to ask any questions through the chat panel. And while we're waiting for questions, I'd like to remind you that this session is being recorded, and it will be available on the UCA website in just a few days, probably within 48 hours. And Mikael, the first question has to do with an early on slide, the diaphragm wall slide. Our attendee asks, how deep does the guide wall need to be?
Well, typically the guide wall is a consideration for trench stability in terms of depth. This is the key aspect. Typically, 3 to 4 feet is enough, but in some cases with quite unstable soils, it has deeper. So an in-depth trench stability analysis has to be done in some cases to determine the depth of a guide wall.
Thank you, Mikael. The next question is, with the custom-built rig for the diaphragm wall, did the clamshell pull the muck one bucket at a time, or was there a pump system to pull the material?
It was one bucket at a time. The pump system that was referred to, I assume, is typically made for hydromill operation. So we didn't use the hydromill in that specific grounds due to the fact that it was a lot of clay that would not be optimal for the hydromill operation in that case. So it depends basically on what type of ground you need, whether it is one bucket at a time clamshell operation or a pump and milling operation with a hydromill.
Very good, thank you. And our next question is, for the SPTC wall, did you place the H-beams after the concrete placement?
So that's a very interesting question. I went quite fast on this. In the unrestricted headroom areas, we placed those beams, that reinforcement, after the concrete was placed, and that was very successful. However, in the restricted headroom area under the bridge, under the I-80 highway, we found out that it was practically impossible to keep the concrete plastic enough to be able to plunge those beams in time without the concrete to set. So that in that case, with beams were placed before the concrete operation.
Okay, very good. And there don't seem to be any more questions. We would invite our attendees to ask any questions of Mikael later using the address on his last slide. And there is one more question that just came in. It says, will Stockton Street be open to traffic after construction is complete?
Yes. It's. I think part of it is supposed to be. The station is supposed to be underground. There will be an above-ground structure, but I believe part of the street will be open. That's again. I'm not. I was not involved with the final design of that station, but I believe so.
Apparently that was from someone who lives near Stockton Street. This does appear to have been the last question. Would you have any final comments you'd like to leave with our audience, Mikael?
Nothing special, really. Just for those of you guys that are working in a design, early stage design of projects. Again, I would invite you to contact us early on. We're always happy to give you our feedback, feasibility analysis, etc. on projects. That's really the main takeaway I have from this, and it helps afterwards during the construction to smooth out the construction process. So again, thank you very much for your attention, and don't hesitate to contact me in the future.
And don't leave yet, because we just had another question come in. How was the QA/QC of the incline pipes conducted for Union Square Station?
So the quality control and quality assurance on the Union Square, like I mentioned, the challenging part was finding a device, which basically we used an existing device and tweaked it to be able to survey the pile's inclination and vertical and alignment. So that was the main challenge for this. The rest of the QC was conducted with standard approaches in the industry, which are typically concrete QC is very important. The excavation and geology quality control is also very important, and reinforcement, right? Those three different aspects: excavation, reinforcement, and concrete, where the emphasis of the QA/QC was on.
And we have another question. Did you have any issues with the inclination of the piles meeting the required tolerance?
So we did not have, fortunately, many issues with this. It's very hard to correct with a pile the inclination. It's possible sometimes early on, but very, very challenging. That's the downside, I guess, of piles compared to diaphragm wall, for instance, where the diaphragm wall is more easily steerable. The variable equipment is more steerable rather than cased piles.
Excellent.
But no, to answer the question, no, we didn't have any issues. Fortunately, I want to say, because the only other option would be to backfill the pile and drill it again.
Ooh. Okay, I think I will say for maybe the third or fourth time that appears to be all the questions that we have. Please be sure to sign up for next month's webinar. The February webinar is going to be excellent, just as this one was. And Michael, Aaron, Heather, everyone, thank you so much for participating. Thank you to all the attendees. And this ends today's session.
Thank you. Bye-bye.
Thank you. Bye-bye.